Welcome to The Explainer. Today, we're going to peel back the curtain on the hidden world of redox reactions. It's this amazing, invisible dance that pretty much powers our entire world. When you see a chemical reaction, it often just looks like some liquids are mixing, maybe changing color or fizzing a little bit. But what's really going on, way down at the microscopic level? Well, it's something way more dynamic and way more fundamental. So at its very core, a huge class of chemical reactions is really about just one thing: the movement of tiny particles called electrons from one substance to another. You can think of it as this elegant, invisible dance that powers literally everything, from the battery in your phone to the very cells inside your body. And that whole process? It's called a redox reaction. It's basically just a mashup of two words: reduction and oxidation. And trust me, if you can get a handle on this electron transfer, you've unlocked a massive piece of chemistry. Okay, so if we're going to call it a dance, then we've got to know the moves, right? Let's break down the two fundamental steps in this whole electron exchange: oxidation and reduction. Now here is the absolute best way to remember the difference. It's a classic for a reason. Leo the lion says "ger." Yup, LEO stands for loss of electrons is oxidation. And GER, gain of electrons, is reduction. It really is that simple. Let's put that into practice. Imagine you have a neutral sodium atom. If it gives away one of its electrons, and remember, electrons are negatively charged, what's left? Well, it's got an overall positive charge now. It becomes a sodium ion. And boom, that sodium atom has just been oxidized. And on the flip side, what if a neutral chlorine atom grabs an electron? Well, now it has an extra negative charge, so it becomes a negatively charged chloride ion. See? That chlorine atom has just been reduced. So here's the absolute key. You can't have one without the other. They are totally 100% linked. An electron doesn't just disappear into thin air. If one thing loses an electron, something else has to gain it. So you can never, ever have oxidation without reduction happening at the exact same time. All right, so we've got the moves down. Now, who are the partners that are leading this dance? Well, for that, we need to meet the agents. Now, I'll admit, this is where the terminology can sometimes trip people up. But stick with me, because it's actually super logical. Every single redox reaction has two main players: an oxidizing agent and a reducing agent. Here's the trick. An agent's name tells you what it does to the other guy. So an oxidizing agent causes something else to be oxidized. A reducing agent causes something else to be reduced. Make sense? Right? But here's the twist. Whatever it does to the other substance, the opposite happens to the agent itself. This is the rule you need to walk away with. Let's just say it again to make it stick. The oxidizing agent is the one that takes the electrons, which means it gets reduced. And the reducing agent, it's the one giving the electrons away, so it gets oxidized. So oxidizing agents, you can also call them oxidants. They're basically the electron grabbers of the chemical world. They're greedy. Substances like potassium permanganate are great examples because they have elements in them that are just really, really hungry for electrons. And then you've got your reducing agents, or reductants, and yep, you guessed it, they're the total opposite. They're the generous ones, the electron donors. Things like oxalic acid are good examples because they hold on to their outer electrons pretty loosely and are more than happy to give them up. All right, so with all these electrons flying back and forth, how in the world do you keep track of it all, especially when the reactions get really complicated? Well, we use something that's kind of like a chemical scorecard. And that scorecard is our main tool, the oxidation number. Now, don't let the name scare you. It's just a number we assign to an atom to help us track whether it's gaining or losing electrons. Think of it like a charge counter for every single atom in the reaction. And using it is super easy. It's just 3 steps. First, you figure out the oxidation number for an element before the reaction starts. Second, you figure it out again for that same element after the reaction is over. And finally, you just compare the two numbers. That's it. The change tells you the whole story. So, think about it. If an atom's oxidation number goes up, gets more positive, what does that mean? It means it must have lost some negative things, which are the electrons. So that's oxidation. And if its number goes down, gets more negative, it must have gained some negative electrons, and that's reduction. It's a perfect way to follow the dance. Okay, so this is all really cool chemistry theory, but you might be thinking, why does this actually matter, right? Well, this electron dance has some incredibly important real-world applications, especially in a field like pharmaceutical analysis. For example, chemists use a process called titration, where they very carefully add one solution to another to cause a reaction. Well, they can use redox reactions to find the exact strength or the purity of a drug. And a critical calculation they use for this is finding something called the drug's equivalent weight. Now, this is a really important detail that the source material points out. The calculation has to be based on the electron change for one single molecule. So for instance, let's say your reaction shows 2 molecules of a drug, losing a total of 10 electrons. You wouldn't use 10 in the formula. You'd use 5, because that's the change for just one molecule. It seems like a small thing, but it's totally crucial for getting an accurate answer. All right, let's do a super quick recap of the whole electron dance. Redox, it's all about transferring electrons. Remember, Leo the lion says jur. Loss is oxidation, gain is reduction. The agents, they always undergo the opposite of what their name says they cause. And oxidation numbers, that's just the scorecard you use to follow all the action. Because now that you know the moves, you'll start seeing this everywhere. This dance isn't just happening in a lab. It's in the battery powering your device right now. It's in the slow rusting of metal. It's in the very way your cells generate energy to keep you alive. It's happening constantly, all around you. Thanks for tuning in to this explainer.